All right, here we're going to work more on graphing some of these other trig functions, the cosecant, the secant, the tangent, and the cotangent. All right, and again with these, I really want you to try to graph them on your own before taking a look at my video solution. All right, so let's first go about identifying these parts of the transformation that are important to us. So we see this pi over 2 here, and it's in parentheses, right? So I know that that is the true shift, right? So we have a shift to the right pi over 2. And then this 1/2, that's our b, right? So that tells us that the period is equal to 2 pi divided by 1/2, right? Which is equal to 2 pi times 2. So we have a period of 4 pi, okay? So that informs us on what we can do to graph this thing. The other thing that we're being asked to do, though, is to also state the domain of this function. And so remember that cosecant is 1 over the sine. So it is going to be undefined anytime the sine is 0. And so remember from our video notes that the argument for what's inside of a cosecant can't be equal to a multiple of pi. And so what we can do to solve this thing is we can go ahead and set the inside and say that can't equal k pi, and then we can solve for that. And of course, remember the reason it's k pi is, because when you look at a sine graph, you have a 0 at 0, at pi, at 2 pi, right, at negative pi, at negative 2 pi. Right? So at all these places, we have 0 as the sign, so you would not want to put that in a cosecant because you'd be dividing by 0. So that's why I set this not equal to k pi. But then, of course, we can solve for that. We can multiply by 2 on both sides. So we have x minus pi over 2 does not equal 2k pi. And then, therefore, x is not equal to pi over 2 plus 2k pi. And we introduced this idea of set notation before, so to make it a little fancier, we could say x such that x does not equal pi over 2 plus 2k pi. So this here is our domain that it's asking us to produce. All right. And we've got these things here set. So one thing that is a nice strategy at times is to, if you're struggling to, kind of stick in your mind what the regular cosecant graph looks like, remember that you can always go ahead and graph the sine function for cosecant and graph that down here, and then that'll help you to appropriately place asymptotes and things like that. So what I'm going to do here is, I know that I want to shift to the right of pi over 2, okay? So think to yourself, well, what would I do if I was to shift the sine function to the right pi over 2, and then also want a period of 4 pi? Well, then what I'd probably do is make it so that this is 4 pi, right? This is pi, 2 pi, 3 pi. So of course this marking right here is pi over 2. And if I take pi over 2 plus 4 pi, that's going to be plus pi, plus 2 pi, plus 3 pi, plus 4 pi. Okay, and right now I'm graphing sine, right? This isn't my actual graph. And then halfway between it, I have another 0. And then, I'd be up at my maximum and down at my minimum here. Okay, and this isn't my real graph, so I'm just gonna, very lightly graph that. And then I can probably go back here, plus pi, or minus pi, minus 2 pi, minus 3 pi, minus 4 pi. So I have a point there, and then halfway between. All right, so there's our lightly penciled in sine function. All right, but here's how this helps us. Now, when I go to graph the real thing, I know that every single place the sine function has a 0, I've got to put a vertical asymptote there, right? Because I do not want to be dividing by 0. And then the other nice feature is at the maximum and minimum values of sine, when sine is equal to 1, right? When you take 1 over 1, you still get 1. So I know that right here, I have the sine and the cosecant of the same value. Down here they do at -1. And then from there, I just need to remember the general behavior, right? I get bigger and approach infinity or negative infinity as I get close to asymptotes. So I've got 2 periods showing here, and that's definitely good enough to get a good idea of what this shifted cosecant, shifted and horizontally shrunk, or stretched, excuse me, cosecant graph looks like. All right, so we're going to do another one here, but I actually, after sending you the notes, decided that I actually wanted to change this problem just a little bit. So let's go ahead and make this change together. So instead of what you see here, I want something similar, but let's do g of x is equal to, and what we're going to do is instead of 3x, it's going to be 3 pi. Oops. Got to write the secant first, don't I? We're going to write the secant of 3 pi x minus pi over 2 and work with that instead. All right, so looking at that, if we want to know our true shift, remember we're going to have to factor out what's inside of there. So I'm going to factor out a 3 pi. This one's a little tougher. You have to ask yourself, what do I multiply 3 pi by in order to make pi over 2 here? Well, the answer is you need 1/6, right? Because 3 over 6 would be 2, and then you would have your pi. So now I can see that this is a shift to the right of 1/6. And then, of course, what's the 3 pi telling me? We know that the period is 2 pi over 3 pi, so the period is 2/3. All right, and then let's do the domain as well before we go to graph this thing. Okay, so now we're thinking about secant, right? The secant is 1 over the cosine. So remember that a cosine graph, when is it going to be 0? It'll be 0 at pi over 2 and 3 pi over 2. Those are the places that it's 0. So it's pi over 2 and then pi in this direction. Then another pi would give you another 0. If you subtracted pi, that would give you another 0. And so what we have here is that argument, 3x minus pi over 2 is not equal to pi over 2 plus multiples of pi. All right, but we can solve this thing. So, oh, excuse me, 3x, I meant to say 3 pi x. I went back to my old problem for a second, excuse me. So 3 pi x. All right, and so I can add pi over 2 to both sides. So this is 3 pi x is not equal to, well, pi over 2 plus pi over 2 is pi plus k pi. And then, of course, we can divide both sides by 3 pi. So we get x does not equal, okay, well, pi over 3 pi is 1/3 plus k over 3. So that's the domain for this transformed function that we're working with. All right, so I have a shift right 1/6, a period of 2/3. You know, sometimes what's nice to do is if you have a shift of a larger denominator than your period, sometimes it's nice to go ahead and get a common denominator. So this period of 2/3, maybe it's worth noting that that's also 4/6, right? Okay, now of course secant is 1 over the cosine. So if we wanted to kind of have a cheater graph to look at to make the graphing of secant a little bit easier, I could definitely graph the cosine function. So let's see, let's do that in we'll do that in green. It's the cosine function, right? But what's happening here? We have a shift to the right of 1/6, a period of 4/6. So I'm kind of thinking that probably what we'll do is, yeah, if we shift it to the right 1/6, yeah, let's go ahead and do this. This will be, each of these will be a sixth. A sixth, 2/6, which is a third, 3/6, which is a half, 4/6, which is 2/3, and then 5/6 here. Okay, so this is our new starting point, but of course, what does a starting point mean for cosine? It means that you're up at your maximum. And then you have a period of 4/6, so you're back at your maximum here, up at 1. And then you're down at your minimum here, halfway between, and then you're at your zeros. But once we get this graphed, and this is totally optional, by the way, if you would rather just remember what secant looks like, then go for it. But a lot of people kind of like this method here because it kind of allows you to start with something comfortable. And honestly, even though you're making two graphs, it's really not much more work, because in identifying your maximum and minimum values, you are definitely, those are the values that are really informing the important parts of your secant graph. So I know that's my vertical asymptote. So is that. And then, of course, I'm going to have one right on the y-axis, which I'm not going to actually draw in there. Oops. sure where that came from. All right, and then from these maximum values up. All right, and I can even put part of one here. All right, so now let's take a look at our tangent and cotangent graphs. All right, so here in example 3, I want to graph the tangent of 2 times the quantity x minus, and there definitely should be a minus there. I'm not seeing. So x minus pi over 4, right? So we can already see this is a shift to the right, pi over 4. And then remember with tangent, here's where we got to be careful, okay? With sine, cosine, cosecant, and secant, we have always taken our b value and divided that into 2 pi in order to find our period. But remember that the period of tangent is not 2 pi, it's just pi. So our period here is pi divided by b. So our period is just pi over 2. All right, we can state the domain. Okay, now here's the thing. Tangent is sine over cosine. So it has the exact same domain as the secant does. So we'll set it up just like in the last problem. We'll set the inside and say that can't be equal to pi over 2 plus k pi. All right, so I can, let's go ahead and multiply both sides by a half here. So we have x minus pi over 4. It should not be equal to, so it'd be pi over 4 plus k pi over 2. But then when I add pi over 4 to both sides, we get x does not equal pi over 2 plus k pi over 2. And that's going to be our domain. But to be quite honest, this is a little bit redundant. K pi over 2 is already a part of that. So you could technically here, and I think it'd be a good idea, although on a test I'd probably not be too worried about this. I'd probably just drop the pi over 2, right? Understand that if you make 1k, you get pi over 2. Anyway, so this encompasses the same information as just saying this, but that's kind of just an aside there. So the important part is getting this thing graphed, okay? So now here's where I wouldn't necessarily suggest writing out sine and cosine on here. I don't think that's as helpful of a trick here. Here I would just ask that you remember what tangent normally does. So it normally goes through 0, 0, and it has asymptotes, well, exactly in those places that the domain is not allowed to exist at. Right? So if you can just kind of remember this general idea here, then you just need to know, okay, if I shift to the right pi over 4, you know, where does my 0 go? Where does my asymptotes go? All right, so let's do that. Let's shift to the right pi over 4. So I'm going to go ahead and call this pi over 4. So then that's pi over 2, 3 pi over 4, and pi. We'll do the same thing for the negatives. Okay, so normally tangent is at y equals 0 when x equals 0. So now it's going to be shifted over to the right, pi over 4. Let me grab a different color here. Let's do green. So I'm going to put a dot right here at pi over 4. Okay, and then the period is pi over 2. So if I add pi over 2 to pi over 4, that's going to be 3 pi over 4. So I know that I have another 0 right here. And then pi over 2 this way, I have another 0 here. Pi over 2 this way, I have another 0 right here. So I know where my zeros are. And then furthermore, I know that halfway between successive zeros has to be a vertical asymptote. So I know that I'm putting that vertical asymptote right here. Vertical asymptote on the y-axis as well that I'm not going to actually draw in there. All right, so now I can draw these in here, and I'm just, you could go back and, test some values out to make sure you're getting where the positive and negative are correctly. But tangent always has this action here where to the right of the 0 it's going up, to the left of the 0 it's going down. All right, so last example here, we'll do another one where we have the argument not factored out, so that we got to deal with that. So this one's going to involve the cotangent. But notice there is a little negative out here, right? So we understand there's going to be a vertical flip. So make a note of that right now. Vertical flip. And so let's take a look what we've got in here. So I can rewrite this as g of x equals the negative cotangent of, let's pull the 2 out. So to get pi over 2 back again, I would have to multiply 2 by pi over 4 to get that pi over 2 back again. So this is going to be a shift to the left, pi over 4. I am going to have, and again, cotangent has a period of pi, so the period is pi over 2, just like our last problem. And then we've got our vertical flip, right? All right, let's also do the domain. Okay, and this will also help us with the graphing, right? So what does cotangent normally do, right? Cotangent normally has vertical asymptotes every pi, and that's because it has sine in the denominator, and sine is 0 every multiple of pi. And then it has this action where it is negative to the left of the 0 and, or sorry, positive to the left of the 0, negative to the right of the 0. So we just kind of got to remember that it's got that general form. So we know that what's inside of there, 2x plus pi over 2, is not allowed to be equal to multiples of pi. So we can solve for x. So 2x should not equal negative pi over 2 plus k pi. And then here what I would say is, since we already have a fraction over here, instead of thinking about dividing by 2, how about we think about multiplying by a half? So this is x is not equal to negative pi over 4 plus k pi over 2. Now I'm going to take a little bit different tactic on this. I've always looked up here first and started graphing, but this domain is a very practical thing to know. Here's what it says. If x can't be equal to negative pi over 4 plus k pi over 2, then what we know is that that's where we're going to have to put asymptotes. All right, so I'm just going to go ahead and do that right now. So at negative pi over 4, I'm going to put my asymptote. I'll go ahead and label it right here. Negative pi over 4. Okay, and then every multiple of pi over 2 from there. So negative pi over 4 plus pi over 2 is pi over 4. Right? And then minus pi over 2 is negative 3 pi over 4. And by the way, all this addition and subtraction of fractions I'm doing in my head here, right? Just, don't be afraid to write that out, right? So, get a common denominator if you need it, right? So for example, negative pi over 4 plus pi over 2. Okay, well, that's negative pi over 4 plus 2 pi over 4. And that's how I knew to put my next asymptote right here at pi over 4. All right, and so we have that. So now we actually know how to make the graph right here, okay? Here's the shift left pi over 4 we were talking about, and you can see that because normally there's an asymptote at 0. And then remember, cosine normally is positive to the left, negative to the right of the 0, but we do have a vertical flip. So that's going to flip everything. So it's actually, it's actually going to look a little bit more like a tangent graph because it's been vertically flipped. All right. And there's our graph of that transformed cotangent function.